So the next functional group that we'll focus on with mass spectroscopy is alcohols. And the reason I'm going in this order because we're kind of putting together things that are very similar. So in the halogen family and in the last one that we did, which was ethers, we said that these two things undergo what we call a heterolytic cleavage and a homolytic cleavage. And they were very similar in what happened. And the homolytic cleavage targeted the alpha carbon in both scenarios. The reason I'm bringing in alcohols at this spot is because alcohols do something very similar to halogen and ethers do. Halogens do the homolytic cleavage. They focus on their alpha carbon and they begin to cleave at those spots. But alcohols do not really do a heterolytic cleavage. You never just chop the OH group off and go away with it. It does something a little bit special. So here I'm going to put an exclamation mark. The reason is because you will think in the beginning that it will be a heterolytic cleavage based on the numbers that we're getting. The problem is that something else is going to happen. And this is really given to those strange little protons that we talked about in the end of the last video. So, alcohols do homolytic. If you're comfortable with that, you'll be able to do these too. Alcohols do hetero in a way, but there's something extra that happens there in order to get them to promote to do it. And we'll see that as well. All right, so again, two options. Very similar to what we've seen before. No big deal. All right, so let me clear this out. Hopefully you know what the alcohol functional group is. And I'm going to start off with a molecule. CH3, CH2, 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 CH, OH, CH3. We're going to start with the homolytic cleavage first. Remember, I said hetero, it's kind of weird. We'll look at that in just a second. But we'll look at homo, we know how to do that. All right, so there's a bond and there's a bond. My alpha carbon, there's the OH, so that's the alpha carbon. And to the left and to the right of that, I could get some cleavage that goes on. And the same thing's going to happen as before. If I cleaved it here, what I would see as a fragment, those electrons would be pulled up in between the carbon and the oxygen. So I would see a CH, CH3 double bond OH with a positive end. There's one fragment. That one fragment weighs about 45. All right, so there's option number one. Option number two, go to the other side. Cleave it. What I have left in that scenario, CH3, CH2, 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 CH, double bond OH up here at the top. Okay, if I do the fragment weight of this one, I add up everything, I'll get a total of 87. So there is my fragment weight. Now notice that in the first scenario, this piece is what will get negative. That will get sucked out of the machine and never be seen. This piece gets a negative. That will be sucked out of the machine. It will never be seen. But there's my two options, 45 and 87. Heterolytic cleavage somewhat can happen, but it's kind of strange. Normally in a heterolytic cleavage, I would just say, cut that bond and away the OH goes. That's what we did with halogens. Cut the bond, chlorine goes away. Cut the bond, bromine goes away. We kind of did that in ethers. Cut the bond and the O and that alkyl group go away. The problem is that if we cut the bond here, the OH goes away. That OH is pretty reactive. I mean, that is a base. So a lot of funny, crazy things can happen in that scenario. And it doesn't really want to do that, right? If that OH is going to go, it's going to make sure that that OH is going to be happy. And it's going to be kind of like a bad marriage. We're getting ready to have a divorce. And that OH group is going to go, fine, I'm leaving, but I'm taking what I'm owed. So it looks at the remaining molecule and it says, what can I take before I hit the curb to make me happier? Well, we keep talking about this alpha carbon. So this is called the beta carbon, and this is called the gamma carbon. Organic is a three-dimensional beast. It's all about the molecule and the shapes. And what happens here is I'm going to redraw this carbon. It's got a hydrogen. It's got two hydrogens. But I'm going to draw one of these hydrogens kind of pointing up here to the very top. So CH2 is what was there. I just erased that 2 and just drawn the extra one kind of pointing up like this. And what happens in the three-dimensional world is that this OH and this hydrogen are neighbors. They might have been seeing each other. No one knew about it until now. But that OH is going to leave, and it's going to go next door, and it's going to peck on their door and say, I'm out of here. You coming with me? Get in the car. We're gone. And that hydrogen says, absolutely. Sure. If that's what you want, I'm gone. And you know what? I don't have to take anything with me. I'm just going to hop in the car. I'm going to leave all my crap here at the house, and away I'll go, and you'll never see me again. And that's what hydrogen and the OH does. So this H and OH will pair up together, and that will end up forming water. So in these molecules, what you typically see, if you want to call it a heterocleavage, you kind of can, but you kind of can't. Because it's not just shaving off the OH group. It's actually shaving off a water molecule. And what you'll have left behind is a CH3, a CH2, a CH with a missing bond now, a CH2, a CH that also has a missing bond, and a CH3 group. This OH has left and took the electrons with it. Because it took the electrons, we get a positive charge. This hydrogen did not need anything. OH promised it all the happiness it ever wants. So that hydrogen leaves everything behind. I told you, it just jumps in the car, leaves, and goes. It leaves behind some electrons, and that's why we always typically denote this with a negative. But it doesn't matter. This is still a positive piece. And that positive piece will still be seen by the detector. It will still be recorded. And what we've done is that we've lost a hydrogen and we've lost the OH. So we needed to subtract 18 from the molecular weight of the compound. And if you go through and add up all the carbons and add up all the hydrogens, this fragment is going to weigh 84. Now, the reason that I'm making such a big deal about the water is because this is a very quick way to determine if we did have an alcohol functional group or not. The total molecular weight here was about 102, and then we would see a peak at 84. And if we subtract these, this would give us an 18 of a difference. That 18 is very specific. It's like the number 15. Every time we've seen 15, it's been like carbons and 3 hydrogens that are tagged along, right? Well, 18 is very particular. 18 is typically assigned to a water molecule. It's a very good indication that I have OH in my compound when I begin to look at the mass spectrum of the compound itself. So, here's the mass spectrum. Notice over here to the end, these peaks are very, very tiny. This is very typical of an alcohol. That means that when the alcohol goes through the electron beam, it doesn't really ever stay together. This thing can easily break apart without a problem. The reason is that this OH has become to be independent. We know that OH is very reactive. We know that OH is very electronegative. OH can be a very good nucleophile for many different things. So OH is very independent and it can be on its own. So if the molecule goes across the electron beam and it gets slammed, OH is not really going to stay there and take the punishment. It's going to easily be ripped off. And it's going to remove a hydrogen when it happens. So because of that, those M peaks are never going to be very, very high. They're always going to be super small. And to be honest, if I was looking at this mass spectra in the very beginning, I would look at those numbers way out there after 100 at 102, and I would look at that number and I would say, well, that doesn't make any sense. Those are really, really tiny. But at the same time, they can't really be isotopes because there's no major lines that are out there for them to be isotopes of. So again, a very good indication that we have an alcohol is to see super tiny M peaks at the end of the spectra. Now, on top of that, you take 102 and you subtract 18 from it. What you'll end up with here is going to be an 84. Well, we see that big number right there, 84. The difference here minus 18 is a very good indication that water is present. Not only that, but see the 84 and the 87, this 102 that's way out here, I see two lines that are basically about the same height. Keep in mind that oxygens have M+2 peaks. So some people would look at this and say, oh, well, 84, 87, that's not an M+2 peak. 84 and 87 are 3 apart. So this is not trying to give you a clue that oxygen is involved. Okay, the same thing's going to happen down here at the very end. Oxygen's involved. There's an M+2 peak. Those things are super, super tiny though, right? So don't be looking at that as a guideline. Furthermore, 84 and 87 are the same height. If that was trying to give you a clue of oxygen, they would not be the same height. One would be much, much smaller than the other one. I mean, bromine's the one that had the same height, the 50% down the middle. Chlorine had a third of the height. Oxygen had even smaller. So that makes no difference at all. Do not use that as a guideline to go by. So 102 is the M peak. We see an 84 that's there. That is minus 18. That's a very good indication that water is present. And now we've went through and talked about how we could get some of these other fragments. Here's what we did before. Here we've identified the 45 group. We talked about how we could form that through the alpha cleavage. And if I go back to the mass spec, here's the 45 number that shows up. And that looks like it's the base peak. This one's the base peak right here. Okay. We also talked about how we got this 87. Well, look, right there's the 87. That's where that number came from. We now know where that one's at. And we now know where 84 is coming from. 84 is coming from the loss of the water, the H2O. Now, what about the 69 and the 57 and the 31 and the 27? Notice when we went through here, we did not do any of those. We got the 45, we got the 87, we have the 84, But we really didn't identify any of these others, 69, 57, 27, 31, that they are identifying on here. Again, the object is not to pick out every single one of these. It's just to pick out enough for us to reason out which one is which. That's all that we're after, and that's all that I'll be asking for. So don't drive yourself crazy trying to figure out where all of these numbers are coming from and which fragments are forming in order to get you those numbers. Okay? All right. So that's the story with the alcohol functional group, and that's the story with how they begin to fragment. All right. So this is where we're going to stop the video. I think that you now understand that alcohols have a tendency to show things that maybe other functional groups do not. One is the loss of water and the loss of 18. The other one is the super tiny M peaks that happen way down at the end of the mass spectrum. No other one has really showed that yet. Alcohol has been the only one. So in the next video, we'll continue on with this discussion. We'll keep looking at mass spectra. We'll keep pulling them apart. We'll keep dissecting them. We'll keep figuring out where these numbers are coming from. That way you'll feel more and more comfortable with this scenario.